Just want to take a copy of the exam there on the way in. As we go along, please do stop me if you've got any queries, anything you want to check, or any related questions, any queries on any of the concepts related to these that we're going through. Okay, so question one, there's only 3 parts here. In some of the years, this has been a 4 parts, 4 or 5 part questions. So it was a little bit different a couple of years ago. So part A is you're given a 2-variable function, cosine of x plus y squared, and you're asked to obtain all the first and second order derivatives of it. Okay, so that's assessing your ability to carry out basic partial differentiation. Then B makes use of the results from part A, and this is about 2-variable Taylor polynomial approximations. So this function, cosine of x plus y squared, you evaluate that at h and k, at least for small h and k, for points close to the origin. Part B claims that it has this simple polynomial approximation, that it's approximately 1 minus h squared over 2. Okay, so that's fairly typical looking small order Taylor polynomial approximation. You're given the general formula for Taylor, or something, well, it goes up to order 2. You're given the definition of this differential operator D that's involved in the Taylor polynomials, and you're basically asked to apply what you've gotten from question 1A into part B and obtain this polynomial approximation. Part C then jumps to the subject of Laplace transforms. As this very key central property of Laplace transforms is how they behave on derivatives. Our main use of Laplace transforms was as a method for solving differential equations. Differential equations feature an unknown function, say g, and some of its derivatives. That's what a differential equation is. The first step in solving them was to take the Laplace transform of the whole equation. So this fundamental property tells you how the Laplace transform of the derivative of a function, how it relates to the Laplace transform of the original function, g. Okay, and it's this nice, direct, explicit relationship between Laplace transform of the derivative of g and the Laplace transform of g. And we're asked to prove that. Okay, so question 1A is assessing your basic partial differentiation skills. You will need to have those, well and practiced and be confident with those for this exam, certainly. You're going to be assessed on them in some, several places through the questions, probably. So here's our function, fxy equals cosine of x plus y squared. Okay, you're asked for all first and second order derivatives. So we'll say there are 2 first order derivatives. df dx and df dy. So we can calculate these. So this is d dx of cosine x plus y squared. And what you're looking to do here is just to demonstrate that you've got a good understanding of the basic principle of partial differentiation. The basic principle is that when you're differentiating with respect to one named variable, here x, any other variables in the function, here y, are treated as if they're constants. So this operator d dx, what it sees here is a function of x. This other, what looks like another variable floating around, this operator is just going to treat that other variable as if it was just a simple number, as if it was 1 or 5, okay, and treat it accordingly. X is the variable that we're differentiating. Okay? So we use that basic principle along with everything else we have from single variable calculus about what derivatives of standard functions look like, and the basic principles, namely linearity, product rule, quotient rule, chain rule, anything else you can think of from single variable calculus. So the derivative of the cosine function is the minus sine function. of exactly the same argument, but we are differentiating a function of a function. You see, non-trivial function of x in here. So we'd have to apply the chain rule as well and multiply this derivative of cosine by the derivative of what the inner function is. But still the derivative with respect to x. Now the derivative with respect to x of this internal of the bracket is going to be 1 plus the derivative of y squared with respect to x. Okay, but this operator treats y as if it were constant, so the derivative of y squared is simply 0 with respect to x. So that, applying the chain rule would just require an extra factor of 1. So I'm not going to bother to write it down. Okay. So that's simply the derivative. The other first order derivative, df dy, again will be d dy of cosine of x plus y squared. And again, it's exactly the same first part, minus sine of x plus y squared. But here, when we're operating the chain rule, we do have something non-trivial to write down, because we're going to get another factor here, which is the derivative of the argument, x plus y squared, the derivative with respect to y. So that's simply 2y. So we'd maybe tidy that up like this. Maybe it's customary to put the other factors out the front and leave the sign bit at the end. Most people seem to write it that way. Okay. So those are the two first order partial derivatives. I wouldn't say it's necessary to name exactly all the properties that you're using. I mean, you might just put in a little comment here using the chain rule. Here it'd be good to see, just to explain the presence of that factor. At least if you do that and you do happen to make a minor mistake along the way, maybe if you're pointing out sensible properties in sensible places, then you may get some partial credit for those. I'm really expecting everybody to fly through this kind of question, I guess. So they're the two first order partial derivatives. There are second order partial derivatives to get as well. And there are 3 second order partial derivatives to find. They are d squared f dx squared, d squared f dy squared, and d squared f dx dy. And you might hear simply mention that that d squared f dx dy is equal to d squared f dy dx. But remember, these things we're talking about operators here. So d squared f dx dy, that stands for the operator d dx, the one on the left, after the operator d dy applied to the argument f. The thing in the brackets I've written down, d squared f dy dx, that on the face of it is something different because it's the derivative with respect to y after the derivative with respect to x. Of f. On the face of it, they look different. It's a different combination of operators, but it was Clairaut's theorem, I think we call it. Not quite sure of the spelling there. Clairaut's theorem, which said that those two, for most reasonable functions, these two second order partial derivatives are the same. So we only have to find one of them. But we got to find them. So d squared f dx squared is d dx of the f dx, which is d dx of minus sine x plus y squared. So we have that from above. So it's going to be minus the cosine of x plus y squared. Again, differentiating minus sine, its derivative is minus cosine, the same argument. You might look at the chain rule then. You got to multiply it by the derivative of the inner the argument to the sign, but that has derivative 1. So I wouldn't write down the extra factor 1. The other one, d2f dy squared, would be d dy df dy, which would be d dy of what we have up here, minus 2y sine of x plus y squared. So what does this operator d dy see here? It sees, okay, a function of y, certainly, but it's presented as a product of two functions of y. So this factor here is a function of y, minus 2y. This other factor, sine of whatever, is a function of y as well. So you got to use the product rule. So this would be using the product rule. All the while using this principle of partial differentiation, that any x's we see here should be treated as if they were constants. So we'll do the product rule. We'll hold the first factor the same, multiply by the derivative of the second factor. We already have that derivative of sine x plus y squared is cosine x plus y squared, but we're differentiating with respect to y, so operating the chain rule would give us another 2y there. Then we hold the sine bit the same, but multiplied by the derivative of the minus 2y. So it's just going to be minus 2, and that still gets multiplied by sine of x plus y squared. So maybe tidying that up slightly, you've got minus 4y squared cosine x plus y squared minus 2 times sine of x plus y squared. Make sense? So we've still got the third second order partial derivative to work out. d2f dx dy, say. This is ddx of df dy. So we've got df dy upstairs somewhere, minus 2y sine of x plus y squared. To differentiate that with respect to x, of course, you don't need the product rule here. The thing you're differentiating is certainly a product of two different functions of y, but as considered as a function of x, it's just some constant here at the front multiplied by sine of x plus some constant. So you don't need the product rule here for differentiating with respect to x. Just go ahead and treat the y as a constant. And you've got minus 2y at the front, and the derivative of sine is cosine, so it's minus 2y cosine x plus y squared. No other factors. The chain rule would apply to multiply by the derivative of the inner bracket, x plus y squared, but it just has derivative 1. So, phew. That's the end of it. So we've got our 5 derivatives in total, 3 second order ones, and 2 first order ones. Boxes there just to emphasize they are tidied up versions. Is that okay? Any queries on those or related aspects to that? And there's 8 marks going there, so that's a fair amount of the 20 marks. So should show, show the detail there, and it's good to indicate the presence of where some of the non-trivial properties are being used, like the product rule, chain rule. Okay. Part B. Part B is working with the 2-variable Taylor polynomial approximations. You're given the formula for it there in compact kind of sigma notation form. And you're given the output that you should be getting. We're using the same function f as is in part A, because it says use the results from part A. So there's 5 marks going here. So we're basically just going to write this summation down, unravel it, and substitute in the necessary parts. Okay? But there's a slight twist here. It's in this. When you see this d to the power n, how do you think of that? See, d is the differential operator. D is an operator. H d dx plus k d dy. It makes sense as an object that you apply to another function. So therefore, the meaning of an exponent, when you put an exponent on an operator, it doesn't mean the operator d multiplied by itself n times. That's not the correct way to interpret the exponent. When you see an exponent on an operator, it means you apply the operator in succession n times onto whatever the object is. So if this is d to the n applied to f, you're applying n of the operators d onto f. So these are n d's here. That's the meaning of the exponent. Okay, so that's important. Seeing people make a mess of this kind of question because they interpret this as just d multiplied by itself, and so they start treating d as if it's a number, but it's not. It's an operator. Okay? So the meaning of the exponents of an operator is composition, not the operation of multiplication, but the operation of composition. D after d after d, appropriate number of times, and the very first d applied to whatever the argument is. Okay, so that's important to know. So let's jump into this. Question 1b. So let's just apply the formula. So f of hk is approximately this. So I'm just going to write down the formula. And whenever in factorial, d to the power n applied to f, and this is evaluated at 0, 0. Yeah, it's kind of important to know how to interpret this here. What it means is it's the operator d to the n applied to f, which is then evaluated at 0, 0. So the evaluation is of this object here after you've applied, after you've differentiated f n times using the differential operator n d. So this is equal to then, so when n is 0, when n is 0, it's simply f evaluated at 0, 0. 0 factorial is 1, and the meaning of an operator to the power 0 applied to something. See, an operator to the power 0 means don't apply the operator. The operator applied 0 times to f, so f is just unchanged. Then you got the n equals 1 term, so 1 over 1 factorial, again 1. You've got d applied to f, and then you've got the evaluation of that at 0, 0. And then the n equals 2 term, you've got d squared applied to f, and then the evaluation of that at 0, 0. Now, where have our h and k gone? Of course, h and k are part of the operator d. You can now bring in the definition of the operator d. This is h df dx plus k df dy. D squared f will give us h squared d2f dx squared plus k squared d2f dy squared plus 2 times hk times d2f dx dy. Now you maybe have memorized that, you maybe know that that's what the operator d squared looks like. If not, that would be a side calculation that you would do to generate that. And if you were a bit hazy on what the correct expression for d2f was, you would work it out like this, that d2 on f is d on f, which is h d dx plus k d dy. So you wouldn't necessarily have to have this as part of your answer, but you might need to do it if you couldn't recall that correctly. And so that's the operator d applied to f. And d applied to f is h df dx plus k df dy. Now, if you expand out these brackets, you're not multiplying these quantities because these things are operators here, so you're applying these operators to that. So this would be h ddx of h df dx, but that would come out as you see h squared times d of df dx, ddx of df dx. Then you'd see when you apply this k bit to this bit down here, you get another k squared and a d dy onto df dy. See, those are exactly the two second order partial derivatives. And you do get two different things for the cross multiple terms. You get a hk ddx on df dy, and you then get a kh dy on df dx. But Clairaut's theorem would tell you that those are both the same. They're both equal to the second order mixed partial derivative, d2f dx dy. So here you're looking at h squared d2f dx squared plus k squared d2f dy squared plus 2, because these are both the same, 2 times hk times d2f dx dy. So yeah, you might need a little side calculation to work that out. Yeah, I forgot the 1 over 2 factorial. Thank you. Is that what you're talking about? Yeah, 1 over 2 factorial. Yeah. So yeah. It's over here. So this should be 1 over 2. That's good. Now I would have spotted that because I would have failed to get the required. I would have got 1 plus h squared, I think, rather than 1 plus h squared over 2. That's a good point. Don't forget the factorial coefficients. And then I should maybe just put a note. I didn't write it in each time, so I didn't want to complicate the expression. But you could just put a note here: all derivatives evaluated at 0, 0. Didn't want to put in bracket 0, 0 after everything, so just make it a bit too long. Too much ink on the page. So is that okay? So that's crucial to get to that stage. And now every one of these functions you've got from part A. Okay, so you can put them in. Okay, so you're now substituting in using the derivatives from part A. So you have to have those beside you, the ones we just did. So f of 0, 0, well, f is cosine of x plus y squared. So this is cosine of 0. So it's just a 1. h df dx. df dx is minus sine of x plus y squared. So when you put in 0, 0, just get 0. So it's h times 0. df dy is minus 2y sine x plus y squared. So again, when you put in x and y both equal to 0, you get 0 times sine of 0. So it's just 0, of course. d2f dx squared, okay, that's minus the cosine of x plus y squared. When you put x and y equal to 0 there, you do get something, you get minus 1. So this gets minus h squared. The d2f dy squared, this one here, that's got a, okay, it looks like it might give you something. So you got cosine of x plus y squared, which will give you 1, but it's got a factor of y in front of it as well. So when y is 0, that bit's all going to be 0. And when x and y are 0, this again is just 0 here. So that's equal to 0. So it's k squared times 0. It's 2hk. d2f dx dy is this one down the bottom. Okay, it looks promising. It's the cosine bit will give you a 1, but again, it's got a factor of y, so it won't. It will give you 0. Okay, that just emphasizes you've got the correct value for evaluating each of the partial derivatives there. And the only thing that remains, the only thing that survives is your 1 minus h squared over 2. That's required. So if I hadn't been reminded about my 1 over 2, I would have just got 1 minus h squared there. And then double check the answer. Of course, it's not that fhk is equal to this, because the first relation up there was approximately. So that this 1 minus h squared is approximately f of hk. Is that okay? Any related questions to that? Okay. 1 part C. Is about our Laplace transforms. So this is just a bookwork proof. But again, not something that you should necessarily learn by heart as such, but just try study the proof of it and try and boil the proof down to some basic principles. Certainly, I would start my answer here by just giving the definition of the Laplace transform. And it's not specifically asked for, but you're going to have to use it in order to prove it, so you may as well declare it nicely. The definition of the Laplace transform Lg of t. G is the Laplace transform of the function g is the integral from 0 to infinity e to the minus st g of t dt. This integral transform, we're integrating this function of a new variable, this e to the power minus s times g of t. Remember, when we were introducing this, we kind of tried to emphasize that the structure of that was somewhat similar to the structure of associating a function called the power series to the object of a sequence. If you have a sequence of numbers, ai, a0 upwards, you can use them as the ingredients to build a function of x, to build an f of x, which is defined as the power series of x, infinite polynomial in the new variable x. See, there isn't any x in the sequence. The x is introduced as a new variable, which is the new variable for a function, and the sequence elements provide the ingredients for the specification of the function. And this is somewhat similar structure here, except we're not starting with a sequence of values. We're starting with the continuous analog of that, which is not a sequence of values, but a whole function's worth of values. So g of t associates one value to every real number t from 0 on. Okay? And this exponential e to the minus st is somewhat similar to this x to the power n here. T taking the place of n. And this exponential to the minus s is kind of taking the role of the new variable x itself there. Where e to the minus s is kind of sitting in the role of this. And this an kind of becomes the function g of t. And summation, of course, the continuous analog of summation is integration. So we explained kind of the motivation for how to think about this thing. So that's the definition. So the property we're required to prove is what the Laplace transform of the derivative of g with respect to t is going to look like. Okay, well, you just apply the definition. We're integrating the exponential e to the minus st, and this is multiplied by the derivative dg dt dt. So there hasn't really been any thinking yet, apart from just knowing the definition of the Laplace transforms. We've just applied it here. And then we look at this integral and we think, what progress can we make with this integral? We don't know anything specifically about the function g. G is a general function g. But what you do see here, and what you should remember as the basic idea here, is you do see this integral set up ready for the application of the principle of integration by parts. Okay? Because it is exactly the integral of some function that has a nice integral, the exponential, multiplied by the derivative of another function. Well, that's exactly the initial setup for applying integration by parts. So we can do that. Using integration by parts, this is going to be the product of the two functions, e to the minus st times g of t. And that's evaluated at 0 and infinity. Come back to that. And then we subtract the integral of g of t multiplied by the derivative of the other factor. And the other factor is minus st, but the derivative with respect to t, because we're doing integration by parts on an integral with respect to t. So we're multiplying by the derivative with respect to t of e to the minus st. So that is, again, e to the minus st, and you get an extra factor of minus s through the application of the chain rule. To the derivative of e to the minus st. Derivative of e to the minus st with respect to t is e to the minus st times the minus s. So that's by integration by parts. And what's going on here? Well, when you evaluate this square bracket at infinity, okay, really you're taking the limit of the square bracket as t goes to infinity. So g might have some behavior as t goes to infinity, but the point was that at least for positive values of s, or if you're allowing s to be complex values of s that had a positive real part, we explained that the behavior of the exponential, which converges to 0 as t goes to infinity for s with a positive real part, but that behavior is going to dominate whatever behavior g has. Because g, we're told, is a function that has a partial derivative. So the original, this integral converges, which means that whatever behavior g has as t goes to infinity, the convergence to 0 behavior of the exponential will dominate. So the square bracket evaluated as the limit as t goes to infinity is equal to 0. Okay. I think we need the real part of s bigger than 0. But. And then you subtract the evaluation at t equals 0. Well, at t equals 0, you simply have g of 0. Because e to the minus st at 0 is just e to the 0, which is just 1. And then you've got this integral here. Now, we're not going to be evaluating the integral, of course. We don't know what the function g is. Can't expect to integrate it. We can see some simplification that's going to happen because this is an integral with respect to t. You've got a product of factors here. If any of these factors is independent of t, you can zip right out to the front of the integral, just to simplify the presentation a bit. Now, g of t has a t in it. E to the minus st has a t in it. But this factor here, minus s, is a different variable than t, independent of t. So that minus s can zoom out to the front of the integral just by basic linearity principle of integration. So the minus and minus are going to cancel. You're going to have plus s, 0 to infinity, and I'll just rearrange these just so they match how they're quoted in the original definition, makes it plainer. So what we've got there here, this integral now you see is exactly the definition of the Laplace transform of g. Okay. So we can write this, we may as well reorder it so it's written as it is in the result. This is s times the Laplace transform of g of t minus the initial value of g, minus g of 0. As required, that's what we were asked to do. Any other parts of it? No, just do that. So, but yeah, so to give a proper answer to that, you really have to quote the definition. You have to use the definition. But beyond that, just knowing the definition and remembering that it's the use of integration by parts, then like even that aspect should be apparent to you once you're looking at this integral here. Because that should say integrate me by parts. Because the product of factors, one of which is a derivative, so it's quite set up for integration. Okay, so that's the end of question 1. I might end there for this morning, but I'll be seeing you 2 more times today in an hour's time, then in Jeffrey Mountain, and then another couple of hours back up here somewhere. So we'll continue working through this, and I'll answer any queries as we go along. Any questions you might have?